Can you guys hear me okay? Okay, great. So today we're going to learn about assembly language and compilers and how we can use both of them in order to take one level of abstraction and convert it into code that can run on our beta. So before we get started, just a couple reminders. The first is that the checkoff for Lab 2 is due tomorrow, so make sure to get those in on time. And the second is that Lab 3 is actually due on Thursday, and so hopefully you've all gotten started on building your ALUs by now. All right, so first, a quick summary of what we learned last week. So what we did in the last lecture is we learned about the beta instruction set architecture and the different pieces of it. So first of all, let's talk a little bit about the storage. So we said that we have 32 general purpose registers. Well, one of them is special in this R31 in that it's always hardwired to the value 0. And then we also have a special register called the PC, or program counter, which holds the address of the instruction that we want to fetch next in order to execute that instruction. So you can kind of think of your, let's say you have this large memory. This is a PC register whose address is pointing to some location in here, and this is the instruction that we want to fetch. And so in main memory, to get a little more into the detail of this, because this is 32 bits wide, that means that since we're using byte addressing, we can access 2 to the 32 different bytes of this memory. But because in the beta, we're always going to access 4 bytes at a time, which is a full instruction, that means that we have 2 to the 30 instructions or locations in this memory that we can access. We have 2 instruction formats for our beta. The first is shown in white here, which is the case where you have 2 source operands coming from registers and then a destination register RC. And the second in yellow is showing the case where you also allow a 16-bit constant to be part of your instruction. And we learned about the various classes of beta operations. So we have, first of all, 2 different kinds of ALU instructions. The first is the one that uses 2 registers, and so that corresponds to this white instruction format right here. And the second is the one that uses a register and a constant as the source operands, and that corresponds to this yellow one over here. And then we have loads and stores, which allow us to access memory. The format of the load and stores is also this yellow format, except that in this case, the constant is used for something else. Specifically, the value of RA plus this constant is used in order to generate the address of the location in memory that you're trying to access. And finally, we have branches and jumps, which also follow this yellow format. And in this case, what's stored in the constant is the offset, which lets us know how far we are from our branch target. Okay, so any questions before we continue? Good. So we have here basically a binary encoding of an add instruction. And as we said, our beta basically expects to get all of its instructions encoded in binary. But so let's take a look at what this thing is telling us over here. We have this opcode, 6 bits of opcode. This particular opcode happens to be for an add. We have RC, which is our destination register, which is telling us that we want to write to register 4. And then we have our 2 source registers, R2 and R3, and then this unused portion. And we mentioned in the last lecture that, it's actually would be easier for us to specify this as something that looks like this, where we say add R2, R3, R4, and the meaning of that is we want to take the contents of R2, add them to the contents of R3, and store that result into R4. We can go even a step further and use high-level languages, where you get rid of the of having to specify, anything about your storage or how you're actually going to go about implementing that particular operation. So here, where we say A equals B plus C, right? I'm not giving you any information about which registers I'm storing B, C, and A in. I don't have to give you any information about the actual underlying assembly instructions that the beta or whichever architecture I happen to have support. Instead, all I'm saying is here's a mathematical expression I want to perform an add, and this allows me to write more concise and easier to understand programs. So today we're going to go through both of these, and we're going to learn how you would go about creating beta code from either form. We're going to start with assembly. Okay, so assembly, basically the goal is to create this binary encoded format that the beta can understand. And, but we want to be able to write our instructions in symbolic form. And so what we do is we have this intermediate program called an assembler. And the assembler takes this symbolic representation of our instructions and converts it into the binary representation. And it knows exactly where to place each of the fields, what the values that need to go into the fields are, and it does all of this work for you behind the scenes. So the most important value of the assembler is that it abstracts away this bit level representation of instructions. And in addition, we're going to see in a second that it also abstracts away the bit level representation of addresses. So for addresses, we're going to be able to use labels, which are just symbolic names, rather than having to keep track of them in terms of numbers. All right, so today we're going to learn about the UASM, or microassembler assembler, which is built into BSIM, which is our simulator for the beta. And we'll go into the details of the some enhancements that it has kind of on top of the basic functionality that make it a little bit easier to code in this assembler. So there are 4 elements to UASM. There are values, which is basically a number. There's symbols, which are a symbolic representation for a value. There's labels, which are just like symbols, except that they're specifically representing addresses. And then there's macros. Macros, we'll get into it in more detail in a minute, but it's basically allows us to convert our assembly form of the instructions into the binary. And in addition, it allows us to enhance our instruction set architecture by creating something that can convert, an instruction that doesn't actually exist, or a form of an instruction that doesn't actually exist, into one that does exist on our beta. And so we'll see that in more detail. Okay. So here's an example UASM source file, and we've color-coded it in order to show the different pieces and highlight the different functionality that is supported by UASM. So let's start off with a green. So the green are comments. So anything that you put in your assembly file that comes after a / is just going to be ignored. Now, we highly recommend using comments when you write your code, because you'll find that if you go away from it for a couple of days, and certainly, if you go away from longer than that, then it's very easy to forget what it is that your code was supposed to be trying to do, and these comments are extremely helpful and save a lot of time as far as being able to, once again, understand what your code is doing. And not only is it helpful in terms of understanding the functionality, but also if it turns out you actually have a bug in your code, trying to identify that bug is much easier with these comments. So in addition to these single line comments shown here, which are just / followed by everything that comes after that, we also have the second form of comments, which is a /* followed by a bunch of text, and then it ends with */. So this allows you to actually do multiple line comments. So if you have something slightly more complicated that you want to explain, you can write several sentences explaining what it is, just simply put it between these two delimiters in order to indicate that the entire thing you just wrote is a comment. Okay, in red we have symbols. So symbols are basically what we've been talking about, which is this symbolic representation of something. In this case, it's a symbolic representation of a constant. Okay, so everything that's shown in red here is just representing a constant. So for example here, this particular algorithm has this notion of something called n. And it's easier for me and more intuitive to write the code here in terms of n rather than saying, oh, this value should always be 12. The benefit of defining the symbol n is that if it's used, for example, in multiple locations in my code, and for some reason at some later point in time I decide that, oh, n really shouldn't have been 12, it should have been 14, well, I only have to come and change it in this one place rather than trying to figure out every single piece of location in my code where I need to change it. It's even more important to realize that every single instance of the number 12 in my program isn't necessarily referring to n. So I can't even just arbitrarily go in and replace every instance of the number 12 if that's how I had chosen to code it. So we highly recommend that when it makes sense to express something in terms of a symbol that you do so. The registers here are also just symbols. So we'll see this in a little bit more detail in a couple slides, but basically R31 is just representing the constant 31. Similarly, R1 is just representing the constant 1. But we use this notation in order to make it a little bit easier for us to understand what it is that our assembly is trying to do. And so when we use registers, we actually put that R notation in front of it, even though the assembler will do the same thing, whether you put it there or not. Okay, in yellow we have labels. And so here we've got the loop. Loop is basically an address of this multiply instruction. And so here in the branch instruction, we later can say, I want to branch back to loop, which is going to take me back to the target of my branch instruction. And finally, we have macros, which are shown in blue. And so macros are used for a few different purposes. The first thing that they do is they basically enable us to take the symbolic representation and convert it into binary. It tells the assembler exactly how to go about doing that. But in addition, it can be used for other purposes, like as I mentioned a minute ago, you might want to create an instruction that doesn't actually exist in your instruction set architecture, but using a macro, you can define it so that you can make use of it in your code. The macro then translates that into something that does exist in your beta, and then you can make use of it from there on in. Okay. So let's take a look at this example here, and let's see what the actual process of assembling this into binary looks like. So the first thing that happens is that we've got this symbol table. So the symbol table is filled in with these pre-initialized symbols. So the symbols R0 through R31, as we just mentioned, are simply constants, which are referred to the constant value 0 through 31. Okay? But in addition, we can add additional symbols in our program like this n. Okay? So as we start to assemble this program, what's going to happen is we're going to read line by line. We're going to start adding symbols to the symbol table and then replacing symbols with their value as we process each of these lines. Okay? So we start over here. We have n equals 12. Note that this is not a variable definition, okay? I can't at some later point in time assign n, to 13 in the same program, okay? This is just a symbolic representation of a constant, okay? I can do what I said earlier, which is if I, change this a particular definition, I can change it to something else, but I couldn't have one line that says n equals 12 and another line that says n equals 14 within the same program. Okay, so when I see this line, it's going to add a value to my symbol table. It's going to say n is equal to 12. I now move on to my add C instruction. And the add C is basically, first of all, has these symbols R31 and R1, which just correspond to the values 31 and 1. And n corresponds to the value 12. And then we have our add C macro, which tells me how do I put all those fields together in order to create something in binary. And so I end up with something that looks like this. Basically, it tells me that my add C opcode are these 6 bits, 110000. And then it does these translations where it takes the destination register R1 and it maps that to a 5-bit value. And so we have 0001 to represent R1 as our destination. We then have the value 31 to represent that as our source operand. And because this is an add C instruction, the remainder of the operation is the 16-bit constant, and you'll see that here what's stored in this constant is the value 12, which has been replaced for that symbol n. Okay? The other thing to note here is that what we show here in black is the location in memory where this instruction is going to go. And so by default, if you're not told anything else, you should assume that your first instruction is at location 0, as this indicates. Okay? We now move on to the next ADC. This is very similar to the previous one. And so again, our assembler is going to produce something of the same form. So again, we expect the opcode to be the same because it's another ADC instruction. In this case, our destination register is our 0, and so we have a 5-bit encoding of the value 0. Our RA is our 31 again, so that doesn't change. And now our constant is just this value 1. Okay? Note, however, that the address where this instruction is going to go is 4 bytes away, right? Because we do byte addressing, but each instruction is actually 4 bytes long. That means that from one instruction to the next, we have 4 bytes going, changing between our addresses. All right, so now we continue and we get to loop. Okay, so loop is this special type of symbol where it's representing a constant that's actually an address. All right, so based on what we learned here, which is that the ADC is at address 0 and the second ADC is at address 4, we know that this loop is going to be at location 8. Okay, so what the assembler does when it gets to this line is it fills in the symbol table the fact that loop corresponds to the address 8. Okay, it then goes ahead and assembles this multiply into binary. And again, we have the similar thing. In this case, this opcode here is for a multiply. We have our destination register is our 0, our source register is our 0. One of them is our 0, and the second one is our 1, and the constant, the rest of it is unused. Okay? And so we continue in this manner, basically converting each instruction to its binary form. Just one note about how the assembler does this, it actually, it assembles each instruction one at a time, but it actually goes through your program twice. The first time it goes through, it identifies all of the symbols and puts them into your symbol table. Then the second time it goes through, it goes ahead and converts the assembly into binary with the knowledge of what each symbol is. So the benefit of that is in this particular example, our symbols were always known to us before they were used. So for example, this loop referred to something that we defined in an earlier instruction. But you can imagine writing a program where you want to actually branch forward, right? So your symbol might not be defined until after the instruction that uses it. So that's perfectly fine, and the assembler can deal with that by doing this 2-pass through the code. Yes? No, this is an actual value of it. So in other words, the symbol R0 is always equal to 0. The symbol R31 is always equal to 31. And the symbol loop is equal to 8. And the way that we figured out that it's 8 is because if we start counting here at address 0, we saw that the ADC is at address 0. The next instruction is at address 4. And the instruction after that is at address 8. Remember that loop is just the address of where the multiply instruction is going to go. So the value of loop is 8. Okay, yes?
So n equals 12, that's just something used by the assembler, right?
Right.
So there's no like physical loading or any of that?
Correct. It doesn't actually end up in any kind of register or memory location or anything like that.
But you still couldn't write like n equals 14 after, and the assembler would be like n equals 12 for the first half, and then n equals 14 for the second half. You can't do that.
No, because basically in the symbol table, it expects to have just a single value for that n, right? Otherwise, it wouldn't know which one to use where. Okay, any other questions? All right. So I mentioned that the registers are predefined symbols, right? So R0 just equals 0, R1 equals 1. And so let's take a look at a little bit more about what the implication of that is. right? So when we take this add C macro here, which says, you know, add the contents of register R31 to this symbol value N, and then store that into register R1, the first thing that's going to happen is I'm going to replace my symbols with their values. Okay, so R31 just becomes 31, N becomes 12, R1 becomes 1. And then I go ahead and expand this add C macro, which tells me how to convert this into this binary. Okay? And so the assembler, you have to remember, is really not smart in any way. So if I was to make a mistake in terms of how I express something, and I said, you know, add R31 comma N, when I really meant to say add C, the assembler is not going to interpret that correctly. It's not going to know that you wanted to use a constant rather than a register as your source operand. Okay, so the key is to remember that there's no type checking here, so you really have to make sure that you understand what it is you're doing. So let's look at a couple examples. So suppose that I meant to do, you know, add of the contents of register R31 to the contents of register R12, store that into register R1. This, however, I wrote add C instead of add. Well, this gets translated into add C 31, comma 12, comma 1, which is exactly what this thing here got translated into. And so in reality, this isn't doing what I was hoping it was going to do. Instead, it's just adding the constant 12 to the contents of register R31. Okay? Similarly, if I had an add instruction when I meant for it to be an add C instruction, then it's going to interpret this value N, which I meant to be a constant, as the index of a register, okay? And so in this case, it's going to interpret this as being the contents of register 12. So even though I meant to add the constant 12, what I'm actually doing here is adding the contents of register 12, okay? So you have to be very careful about making sure that you don't have these kind of typos in your assembly programs. Okay, so now we can go back to this program and see, talk a little bit about how the branches are going to look. And if you remember in last lecture, we talked about the fact that we compute this offset, and the offset is what's stored in your actual instruction. But the calculation of this offset is a little bit hairy. Oops, it looks like that. And so it's nice to have the assembler do this for us and for us not to have to worry about it. All we have to do is just say, oh, I want a branch to loop. The assembler will figure the rest of it out for us. But what it's actually doing is it's counting the number of words away from the instruction that immediately follows the branch. So the instruction that immediately follows the branch is over here. To get back to the instruction whose address is loop, I have to go back 1, 2, 3 instructions. And so I expect my offset to be -3 because I'm going backwards. If I was going forwards, it would be a positive number. Okay? And so when I look at the actual assembled value of this branch operation, this is the opcode for a BNE. This is just my destination register, which is R31. This is my source register R1, and here, this is a 16-bit constant representing the value -3. Okay? Okay, so macros. So we said that macros are used in order to tell the assembler how to convert an existing an existing instruction into binary. But in addition, we can use it in order to make our lives a little bit easier. So for example, if you look up here at the top, you'll see that, you know, we don't actually have a load instruction that can specify here's an address of a location that I want to get something from and load it into RC. Right? The way we actually have to specify that is we'd have to say load R31 comma this address CC, and that gets loaded into RC. And so in our macros, we can actually just define something which allows us to use this form of the instruction as well. And so this makes it a little simpler and more intuitive when we write our programs if I don't have to explicitly remember to put that R31 when all I wanted to do is get the value that's at this address CC. Okay? Similarly, I might not want to always do conditional branches, okay? If I want to do an unconditional branch, the way to do that in the beta is you have to say branch on equal R31 to some label, right? R31 is always equal to 0, which means that this is going to unconditionally branch to this label. Okay, so it's easier for me to think of an unconditional branch in this form. I can write just branch to label, and then that gets translated into this, which is an actually existing operation in our beta. Okay? And a couple other useful macros are if you're doing things like comparisons, like let's say I want to check if A is less than B, then I want to execute a sequence of operations. Then my compare operation would do, the A less than B and store the result of that in a register. The result is either 0 if it was not less than B, or 1 if it is less than B. And so then it kind of becomes intuitive to say, okay, depending on which way I wanted to look at that comparison, I can either branch on true of that result value, or I can branch on false of that result value. And finally, the other thing that you can do with macros is that you can actually use it in order to specify a group of instructions that need to be executed together in order to implement one particular operation. So we won't get into the details of what these push and pop instructions are until next lecture. But the key right now is just that this translates actually into 2 separate beta instructions. Okay, so we've seen how we assemble instructions. Now let's think about how do we deal with data. Okay, so data comes in 2 forms, all right? It can either be in a variable, or it can be some kind of constant that we can't represent in our 16-bit constant, and so instead we have to store it in memory somewhere. So here we have an example of 2 situations. We've got here n equal to 12 being used as a variable here. And we have fact n, which is where the result of this piece of code is going to go, which is set to this thing over here. So in our symbol table, what happens? Okay, n and fact n are just addresses. Okay, they're just locations in memory. And so because this is the first line in our code, n translates into location 0. Fact n translates into location 4. So in my symbol table, I just have n is equal to 0 and fact n is equal to 4. Now I go to implement this load instruction where I'm trying to say load the contents of what's stored at address n into R1. So because of my macros, that's going to translate into load R31 comma n comma R1. And what that tells me to do is take the memory location that's specified by the contents of register R31 plus this constant, which happens to be 0 from the symbol table. Okay, and so what that means is that I'm adding the value of register R31, which is 0, to 0, and I'm getting my address 0, and so this is telling me get the location, get the value that's at address 0 and put it into register R1. And that value is this 12, which I have right here, because this is my address 0 of my program. Okay? All right, a couple other things are expressions. So our assembler can actually specify things like a equals 7 plus 3, and that will actually be figured out for you by the assembler itself. So it's not that it's going to create a beta add instruction. Instead, it's simply going to associate a with the result of having executed this expression. And finally, the last thing, which is very useful, is this dot or period symbol which we use. And dot basically means it refers to the next location in memory that we're going to fill. So if I say dot equals 0x100, it means that the thing that immediately comes after it is going to be stored at location 0x100 in memory. I can also say things like k equals dot, and now the next location I'm going to fill is 0x104, so that means that k is equal to 0x104. And finally, I can also say things like dot equals dot plus 16. This allows me to save some space in memory for an array, for example. So suppose that I have a 4-element array. Each of those elements is 4 bytes, so I need to save 16 bytes. So that's exactly what this is doing here. Okay? All right, so just very quickly, just to summarize what we've learned is, so we have 4 elements in our microassembler. We've got the values, symbols, labels, and macros. We saw how we go about converting each of those into the binary encoding, and we also learned how to make use of this dot symbol. Okay, so now we're going to change gears, and we're going to go back to our first slide, where we said, well, yeah, it's definitely easier to express this binary encoding as add R2, R3, R4, but wouldn't it be easier still if I could say something like A equals B plus C, okay? And not have to specify anything about my instruction set architecture details when I specify this high-level operation that I'm actually trying to perform. So let's take a look at how that works. So here we have a well-known algorithm, which stands for, GCD stands for greatest common divisor. And basically it allows you to very efficiently specify how you would go about finding the GCD value of 2 numbers, x and y. Okay? You don't have to worry here at all about writing assembly code. Instead, you can just at a very high level specify what it is that you want your algorithm to do. And so the benefit of this is that we can write much more concise and more easily understandable code to express what it is that our algorithm is trying to do without worrying about the details of the underlying hardware that's going to ultimately run this code. Okay, and so in 6004, we're going to use C as this high-level language. There are many, many high-level languages. There's Python, there's Java, lots of others, but we've picked to use C for 6004. Actually, we are using a simplified version of C, and for anybody who wants to look for a reference in the handouts portion of the web page, there's a simple reference to anything you would need to know about C for this class. Okay, so what are the advantages of using a high-level language over assembly? So, as I mentioned, first of all, our code is going to be much easier to understand, right? It's much easier for me to express my algorithm in this form than to have to convert my while loop into assembly instructions and then interpret what it is that those assembly instructions really mean. Similarly, it's also more readable, and it's more maintainable and easier to avoid having bugs in it. The other useful thing about high-level languages is that we can do something called type checking, okay? So we mentioned with the assembler is that it was really stupid, right? If I use the form add C instead of add, then I might be doing something completely different from what I expected to do. In compilers, they do a little bit of this checking for you. So it does some type checking, and it says, you know, if you're trying to use a constant where you should be using, let's say if you're trying to use a string, for example, data type, where you should be using an integer, it can identify that for you and flag that as an error. And so before you even begin to run your program, you can very quickly identify early problems with your program so that once you get to the actual debugging process, you're much further along in having produced a valid program. Okay, and then finally there's portability, which is that when I write this program in a high-level language, I can run it on any processor, right? As long as I have something that translates from this high-level language to the processor, this algorithm continues to be valid. All right, so then we want to ask ourselves, well, are there any disadvantages? In other words, if I was to painstakingly write my assembly code in such a way that I always optimized it to the extreme and I got, every little bit of performance out of it, aren't I going to be, in a better situation as far as performance goes than what I'm going to be able to achieve from this high-level language? And the answer to that is that it actually depends on how you go about implementing this. So there's two different ways one can go about this. One is called interpretation, and one is called compilation. We'll get a little bit into the details of what these mean. And then we're going to look a little bit more closely at how one would actually build a simple compiler for our beta instructions, for converting C to our beta instructions. So the way interpretation works is, imagine that you have this hard-to-program machine M1. You want something that's easier to program. And so what you do is you create a program called an interpreter, which basically mimics the behavior of another machine, M2, that's much easier for you to program with and much easier for you to work with. And so essentially, by putting this program together with M1, you've created an emulator for this machine M2. And so every time you execute one of these M2 operations, it's actually really executing maybe a sequence of M1 operations. You can actually have multiple layers of interpretation. So for example, suppose that I have, an Intel CPU. And on top of that, I want to run a Python interpreter so that I can write my program in Python instead of writing it in the assembly language of an x86. Okay? And then I could have yet another level of abstraction where the Python calls this toolkit, which is called SciPy, and what it does is it's very good at dealing with large matrices of numbers and doing number analysis on them. And so a single instruction in SciPy can amount to multiple Python instructions, and then each of those Python instructions could amount to many, many x86 instructions. But the idea is that by allowing these levels of interpretation, I can make the description of what it is that I'm trying to do much easier. So the place where interpretation is very good to use is when we're not so worried about efficiency of our ultimate performance. So if I'm analyzing an algorithm and I want to get a quick sense of does this algorithm work or not, interpretation is a great way to go. And so I can use a language like Python, which uses an interpreter in order to run the code. However, if I'm at the point where, okay, I know this is what I'm trying to achieve and I want to get the best performance out of it, in that case, using interpretation is probably not the way to go, and instead, I want to use compilation, okay? So the way the compilation works is, again, I've got this hard-to-code machine M1. I now have a program P2 that's written in a language that's easy for me to work with. And then I have this compiler which translates this program that's written in this language L2 for P2 into a program that's written in the machine language of M1 so that it can run on M1. So a couple things to notice about compilation. The first is that your actual compiler can run on any machine. It doesn't have to, like in the case of the interpretation, the interpreter was actually running on your M1 machine. Here, this could be your M1, M2, or even some other machine altogether. The second thing to notice is that here we're separating, we're making two steps in our compilation process. The first is processing the input data, and so that's converting P2 to the P1 form. And then anytime we actually want to execute our program, we're only going to run this P1 program, which actually runs M1 instructions. We don't need to repeat this step over and over again, okay? So both interpretation and compilation are used very heavily, and depending on what it is exactly that you're trying to achieve, you might choose one over the other. So just to quickly summarize the difference between the two is, suppose that I have, an expression x plus 2. If I'm using interpretation, the way that that's going to work is I'm actually going to take the value of x, add 2 to it. and I'm going to do that as I'm executing the program. In compilation, I'm not going to do that. Instead, I'm going to generate a program that has the ability to add x and 2. And so it's going to know how to fetch this operand x from memory and then perform an add c instruction in order to ultimately execute x plus 2. So as far as when these things happen, in interpretation, it's all happening during execution. Okay, so you're doing both the processing of what it is that you need to do as well as the execution at the same time. With compilers, you're splitting up those two tasks. Okay, so first you're processing it, you're converting this P2 program to P1, and only after that do you run P1. The benefit of that being that when you run P1, it can be much more efficient because since you're only paying this cost of processing once instead of every single time you're running it, you can actually make your compilers very, very intelligent, where they spend a lot of time analyzing the data and what you can do in order to optimize it and get the most efficient code possible. Okay, and finally, decisions in interpretation are made at runtime, whereas in compilation, they're made at compile time. This is actually a case where interpretation kind of wins out a little bit because you're leaving the decision till later, you can actually support much more flexible things with interpretation. So for example, you might be able to use the same piece of code to handle different data types, whereas in compilation, you'd have to have two separate pieces of code, one for each of those. Okay, so just to summarize that, as far as which one we use, we are going to want to use interpretation when we're in the mode that we're probably only going to execute whatever this program does once, and we're just trying to, evaluate whether a particular algorithm is good or not. If we're in the situation where we want to execute something many times, then it's probably worth paying that upfront compilation cost in order to end up with a more efficient program. And then from then on, I would run the efficient program. Okay, so let's take a little bit of a closer look at how we would compile basic C expressions into the beta assembly language. So we have this compiler, which takes C in, produces beta assembly instructions out, and there are a few things that any good compiler is going to do. The first thing is type checking, which we mentioned earlier, right? So if, for example, I have an instruction where I'm taking two variables and I'm trying to add them together, and it turns out that one of those variables is associated with a string and the other is associated with a number, where my compiler is going to be able to identify that error and say, hey, something's wrong here, go fix your code. All right. So let's jump into how we actually might go about creating assembly from a high-level language. Okay, so we're going to have two pieces of code that we're going to run. The first is compile statement. So in our programs, we have many statements, and so clearly we're going to run this compile statement repeatedly. And the type of statements that we're going to look at are the following. We might have an unconditional statement, which is always executed, and it's executed once. We might have what we call a compound statement, which is a sequence of statements executed in order. We might have a conditional situation where we're going to evaluate this expression, and if it's true, we'll execute statement 1, otherwise we'll execute statement 2. And we might have iteration, where again, we evaluate this expression, and as long as it's true, I continue to execute these statements. Okay? The second piece that we're going to have is compile expression. The types of expressions that we can have are, well, let's say I can have a constant. I want to be able to somehow get this constant into a register so that I can then use it by the statements. We'll see how to do that in just a minute. I might have variables. I can either have scalar variables like, A or B, A or C, let's say, or in this case, B is an array element. And so it's slightly more complicated in that I first have to evaluate this expression in order to determine which index of my array I'm trying to access. I also have assignments where I evaluate an expression and then assign it to a particular location in memory. We have operations where I can take one expression and add it or do some other kind of mathematical operation to get between these two. And finally, we have what's procedure calls, which we're not going to get into today. That's going to be the topic of next lecture. So let's take a look at what compile expression and compile statement are actually going to look like in detail. So suppose that I have this constant, 1, 2, 3, 4, and I want to load it into register Rx. Well, what might that look like in assembly in our beta? There's two possibilities. I can either have a situation where I'm using this macro cmove to move this constant 1, 2, 3, 4 into Rx. This simply translates into an add C R31, 1, 2, 3, 4, Rx instruction. And here I'm able to use this because this constant is not so big, and so I can put that constant in my actual instruction. I might have another type of constant which does not fit in 16 bits. So in that situation, I'm going to have a memory location that holds this constant. And so this label here, C1, is just a label specifying where is it that I'm holding this constant. And then I need to do an actual load operation in order to read the contents of that location, C1, and put the value into register Rx. Okay, so that's how I would deal with constants. For variables, if I have a variable A that I want to put into register Rx, it looks similar in the sense that this is a location in memory that's going to store my variable A, and I'm going to then need to do a load of the contents of what's in location A into register Rx in order to make use of that variable. In the case of an array element, it's a little bit more complicated in that I first have to run compile expression on this inner expression and get that to put the value of this expression into a register so that I can make use of it. Once I've done that, then the way that I access this array element is by multiplying this index, which I just computed, times the size of any element of my array. Okay, so if I want to access index 2, and there's 4 bytes per element, then that means that I want to access the location that's 8 bytes away from the beginning of my B array. Okay, and so what we see here is we store location, we have specify a location where we're going to store this B array, and it says that starting at the next available memory location plus B size times B length, that's going to give us enough memory storage for B length elements of size B size. Okay, and so now once I have this index, I can simply multiply that index by B size and then load the address B plus this value of the multiplied index into Rx in order to get the value of B sub I. Okay? And we move on with expressions, with assignments. And so suppose that I have A equals expression. What does that translate into? Well, again, it's going to be a recursive call. So first I call compile expression on this expression. I evaluate it and I get the value into Rx. Once I have it in Rx, then I do a store of this Rx that I just computed into my variable A. And that's going to take care of my assignment type of statements. And finally, operations, if I have expression 1 plus expression 2 should go into Rx, then I'm going to want to do compile expression 1, then compile expression 2, and then add the result of those in order to produce the result I'm actually trying to achieve. So quickly, let's walk through this example. Suppose that I have this really complicated example. We want to go ahead and compile this. Okay, so I start off with this assignment, and then I'm going to take a look at just the right-hand side of this. And so I have an expression which is just the right-hand side. Then I have to divide this up even further. And so that's going to tell me to call compile expression on just x minus 3. And then I'm going to take it even one level further, which is compile expression x. At this point, I can convert this into an assembly instruction, which is just load x into R1. Okay, so now I've got my x. The next thing I need to do is compile this 3. So this is also going to be another assembly instruction where I'm moving this constant into register R2. Now I'm ready to do my subtract operation of x minus 3. So x is in R1, 3 is in R2, and so I do subtract R1, R2, store that result into R1, and I continue in the same manner. And so you'll see that if we follow this through, we've got basically the description of this y plus this long constant. And finally, we add those two results together, and then we multiply this expression times that expression and store that result into y. Okay? So there's just a couple more slides I'll finish off next time. But basically, this gives you an idea of how it is that we went about taking this high-level code and converting it into assembly language that can run on the beta. And over here, we've got our memory locations, which are required to store our variables. Okay? All right, see you next time.